Okay, so I want to evaluate this line integral. Okay, so this is going to be the integral, and then I put in my t-bounds, so I have from 0 to 1 of f of r of t dot dr. So, or people usually just write this as f, excuse me, dot dr. Okay, so the 0 to 1, that's our bounds for the parameterization. So let's actually evaluate this. This is 0 to 1, f of r of t. And what is dr? Well, the easy way to do that, to think about that, is if I multiply and divide by dt. So this is dot dt. Okay, so now let's plug these in. What is f of r of t? Right, I want f in terms of t. Um, Sine of x, well, the x component is t cubed. So this is sine of t cubed. That's the I component. Plus the j component is cosine of y, which is minus t squared, plus xz. So x was t cubed times z, which is t. Right, so this is my x, y, and z, and these are the things I'm plugging it into. Okay, and then I need to know what is dr dt, right? That's just r prime. That's going to be 2t squared minus 2, that's I, minus 2tj plus 1k. Alright, so if I do the dot product of these two vectors and plug this in, see, is that right? Okay, so if I do the dot product, I get the integral. Wouldn't it be 3 on the first? Yes. Okay, so if I do the dot product of these two, I get 3 sine, or 3t squared sine t cubed, there's no I because I'm doing a dot product, minus 2t cosine of negative t squared plus t to the fourth. Okay, and this is what I want to integrate. This looks possible, right, because I can do this kind of u sub for each of these first two terms. So here, let's see, cosine of negative t is the same as cosine of t. So let's just put cosine of t squared. Okay, so if I do this first integral, I set u equals the t cubed. So du equals 2 or 3 t squared. Okay, so here I can plug that in. Right, this is du, so I just integrate. So that's from 0 to 1. Then here, actually, I could have left that as negative. That probably would have worked out better. Yeah, let me leave that as negative, because the derivative of that is just, let's see, so minus 2t. So if I do u equals minus 2t squared, or sorry, minus t squared, minus t squared, du, that's the same thing. Let's see, so that's minus t squared minus 2 t, right, that's the derivative, which is this right here. So I can write this as plus the integral from, at 0, this is 0, this is becomes negative 1. So from 0 to negative 1 of cosine of u du, and then that doesn't need a transformation. Okay, so integral of sine of u, that's going to be negative cosine of u from 0 to 1, plus integral of sine, or cosine is sine from 0 to negative 1, and then plus t to the 5 over 5 from 0 to 1. Okay, and then I evaluate these, so I have minus cosine of 1 plus cosine of 0 plus sine of negative 1 minus sine of 0 plus 1/5 minus 0. So this is equal to 1, this is 0, this is equal to negative sine of 1, right? For sine, I can, sine of negative x is the same as sine of negative sine of x. So this I can write as negative cosine of 1 plus sine of 1 plus 1/5. No, sorry, plus 1 plus 1/5. That's going to be plus 6/5. Okay, and that's how I do the line integral of a vector field. Okay, so I'm given a vector field. I'm given a curve that I want to integrate this over. And again, remember what this actually corresponds to. Right, so I want to kind of, so I have this vector field. They're kind of doing whatever, going in whatever direction they want. But if I have a curve along the line, I want to add up the components of these vectors in this direction, right? So I kind of want to add up the components of each of these vectors as I go along this curve. Okay, so yeah, okay. Think of this as like the projection of f onto this curve, and I'm integrating all of those projections together. So I'm adding all of those projections up. Okay, and I will do one more. I'll do one more to remind you of how to do this on a for a scalar function, right? So that was for a vector field, and if I want to do it for a scalar function, that one looks interesting. Let's see if I can do that one. Here we go. Okay, so this one is different, right? This one, my f is like this. This is a scalar function, right? So I put x, y, z in, and it gives me a scalar out. It doesn't give me a vector out. So this isn't a vector field, it's a scalar field. Okay, so it says integrate this along this curve where this is the line segment. Okay, so first thing I need to do is I need to parameterize the line segment. Okay, and there's an easy way to do that. So if I go r of t, I do t times the first one, times the first point, plus 1 minus t times the second point. 1, 2, 3. So if I have 2 points, this is, I'm sorry, I did that backwards. This is supposed to be 1 minus t in front and t right here. Okay, so if I write this anytime, this is going to give me a parameterization of the line between these 2 points. I really don't care what 2 points it is. If I do this to them, it's going to give me a line between 2 points. At 0, right, when I plug in 0, this is 1 and this is 0, so I get this point. So at 0, I get the first point, and at 1, I get the second point, right? This is 0, this is 1, so I get the second point. So this is also nice because I know that for the 2 points, if I just want from here to here, this means that t starts at 0 and goes to 1. Okay, so I can simplify this a little bit. This is all zeros, so my r of t is just t, 2t, 3t. Okay, so to integrate a scalar function like this, integral of f of x, y, z ds. So ds, again, remember that stands for a small segment of the line, right? I have some curve, and ds represents the length of a small segment. But we also said that this was equal to the integral of f of x, y, z. So what is ds? That's ds dt times dt. And ds dt is equal to the norm of r prime of t. And I'm going to be integrating this from 0 to 1. And actually now I don't want to evaluate this at f of x, y, z. This is going to be evaluated at r of t. Okay. So let's go ahead and plug these in. So I need to find the norm of r of t. So, sorry, r prime of t. So r prime is 1, 2, 3. And the norm of that is square root of 1 plus 4 plus 9, which is square root of 14. Okay, and then I need to integrate this function. So I need to plug in, so f we said was x e to the y times z, or e to the y times z. So if x is t, right, so this is my x, this is my y, this is z. So if I plug all this in, I have an integral from 0 to 1 of t e to the 2t times 3t times root 14 dt. I can simplify this. I have the root 14 in front. Integral 0 to 1 t e to the 6t squared dt. Let's do a u sub. U equals 6t squared. Du equals 12t dt. Okay, so we plug all this in and we get that this is equal to root 14 integral 0, 1. So I have e to the e to the u. So I need to I have t here. I need to multiply and divide by 12. So then I have 12t dt. This becomes du. And finally, I have 14 over 12. Integrate this, and I get e to the 1 minus e to the 0 for a final answer of root 14 over 12 e minus 1. Okay, so that's a quick refresher. Let's see, how do I Know that the bounds are from 0 to 1. Okay, yeah. So that's my final answer. So how do I know that the bounds are from 0 to 1? So first off, I know that I'm going to pick any 2 points. Okay, so basically if I draw a line through these points, move that up. If I draw a line through these 2 points, the first thing I know is that it's only going to pass through each of these points once. So I don't have to worry about there being like multiple times where this line crosses these points. Okay, so if I write r of t in this special way, right, I just do a combination. So the first point I multiplied by 1 minus t. So this is actually a really useful trick. I'm glad you asked this question. Okay, so I do 1 minus t times the first point, right? So this is going to be, this is p some point, and this is some other point q. Then I can write this line as p times 1 minus t plus q times t. And that's going to describe this line. Okay. Because notice, when t is 0, this is 1, so we get so 1 times p plus 0, right? T is 0, so this whole term is 0. So at t equals 0, I get that the line, or we just get, our point P. So we start here at t equals 0, and then because I wrote it in this way, I can do at t equals 1, right? This is 0 now, and this is 1, right? So I just have r equals q. Right, so from 0 to 1, I get P to Q. And this is going to work no matter which points I get. So if you have to parameterize a line, I highly recommend doing it this way. Okay, so that's all I'm going to do on line, well, I mean, we're going to do some more on line integrals, but on actually just evaluating simple line integrals. Okay, so next we're going to go to we have a name for it? The fundamental theorem of line integrals. Okay, so yes. Yes, that is correct. If you get this backwards, like the 1 minus t and t, all that means is you're going to be starting here and going here instead of starting here and going here. So, okay, so first thing, does anyone, so I have a vector function, a vector field. Let's see how to write this. I'm just going to write this as a vector field. Okay. And I want to find the derivative of this along some line. Right, so I have some curve r of t, and I want to find the rate of change of this function as I move along this line. So I want to find d dt f of r of t, right? So if I only look at the xyz points along this curve, I want to find the rate of change of this surface. So if you remember, I have to do the chain rule for this, and what I get is that this, I'm sorry, this is not a vector field, this should be a scalar field. Okay, so here what I get is that this is going to be equal to the gradient of f at r of t times r prime of t. Okay, so I just want to remember that fact for a second. This was from a couple sections ago. Basically, it was just the chain rule. So now, let's see. So now, let's also remember another fact. If I integrate a derivative, so this is just a regular derivative from a to b of like this, what do I get? If I integrate a derivative, or I just get the function back, right? It kind of just undoes the derivative. Integrating a derivative kind of undoes it. So this is just going to be f of b minus f of a. Okay, so here, if I can write this as a derivative of something with respect to t, and then I integrate with respect to t, right? I can just evaluate this integral very quickly by just plugging it into the endpoints. Okay, so this makes it, if I can write it as a derivative, right, integrating becomes very easy, right? Integrating a derivative is quite simple. Okay, so let's put these two ideas together. So here, if I know that I can integrate a derivative very easily, and this is my derivative. Um, so this is f of r of t. So from this, dt, from this right here, we know that this is equal to what? This is equal to f at r, so I should put like t0 and t1, probably better numbers. I'm not sure what those. No what? Right, this is just the application of this right here. Right, I just plugged in the top bound, and I just plugged in the bottom bound, and I get this. Okay, but on the other side, right, I know that this is the same as this. Okay, so this should be equal to the integral from t0 to t1 of gradient of f dot r prime of t dt. So another way of writing this is the integral of gradient of f dot dr. Okay, so this is the over some curve. Okay, so here, if I'm integrating a function, doing the line integral of a function that is a gradient, right? So if I can write this as a gradient of something, then it becomes really easy to evaluate. Right, I just evaluate it at the two ends of the curve that I'm interested in. Okay, so yeah, so just compare that with doing a regular line integral. So what we're going to be interested in a second, let's see, so we have f dot dr. Right, so we're interested in trying to work these out and try to find easy ways to work these out. So one thing I can do is if, big if, f is equal to the negative gradient of something, and the negative, we'll see why in a second. It's not terribly important for this right here. But if I can write f as the gradient of some function, right, if you remember, we worked out a bunch of these problems a couple weeks ago. You know, when can I write a function as a gradient? So if I can do that, then the integral over this curve, f dot dr, is just equal to, well, this was going to be equal to that, and this is equal to f at r of t1 minus f at r of t0. Right, basically I just evaluated on the two endpoints. Okay, so let's look at something a really fascinating side effect of this. So an interesting side effect is that if I want to evaluate a line integral from here to here along some curve, right? I know how to evaluate this integral, this line integral, right? Evaluating this over this curve. I just subtract the values at the two endpoints, here and here. So that means that it didn't depend on the path that I took at all, right? So if my curve was this, or if my curve was, I don't know, something like this, I would get the same result for this integral. Okay, so this is a kind of a strange thing, right? Where the path that I take, that I integrate along, it doesn't matter if this is true, right? If I can write f as the negative gradient of something. Okay, okay, so let's see a quick example and remind ourselves how to check if something is a gradient or not. Okay, so if I have f of, let's see, actually, can I copy this? I can. That's easier. Um, okay, and erase that. So I have um, two vector fields here, and I want to know which of these can I write as the gradient of some other function. Okay, that's some other function. So I want to find, I have this, and I want to find this. This they call a potential function, and we'll see why in just a little bit. Okay, so the way I do this is assume that f is the gradient of something. So that would mean that um, df dx is equal to 2x minus 3y, and df dy is equal to minus 3x plus 4y minus 8. And then I need to check if the mixed derivatives are the same. Okay, so here I need to check that the y derivative of df dx, well, what is that? That's minus 3. And then here I need to check that the x derivative of this one is also the same. So that's 0, this is minus 3. Since these are the same, right, when I switch the order, sorry, this should be, yeah, that's right. Since these are the same, I know that this exists, right? I can write this as something. And how do I find that? I do that by integrating each of these. Okay, so if I integrate t minus 3y, I integrate this with respect to x from 0, no, just antiderivative, I get, what, x squared minus 3xy plus some constant with respect to x. Okay, so that means that this could be some function of y, right, because this would vanish if I did the derivative with respect to y, plus some constant. Okay, and now I do the same thing with the other component, except now I integrate with respect to y. And this gives me minus 3xy plus 2y squared minus 8y plus some function of x plus a constant. Okay, so now I'm going to compare these two terms. And first I'm going to, so here it tells me that f, oh actually let me just forget the negative for a little bit. It's not important for now. Okay, so first I'm going to look at what are the functions that involve only x. Actually, no, I'm sorry. What are the functions that are in both of these, right? So that's going to be this and this. Okay, so that's going to be there for sure. Now I look at what are the functions that involve only x, right? So these are functions that involve only x. So here we see that the only one we have is going to be x squared. So that tells me that this function of x needs to be x squared. And then I look at functions involving only y. That looks like it's going to be this. And then I have plus a constant at the end. Like this. Okay. So if I wanted to evaluate the line, okay, so when this is possible, if that's possible, we say that F, big F, is a conservative field. Okay, so we say it's a conservative field when we can write it as the gradient of something else, as the gradient of some potential function. Okay, I'll do one more. So that's e to the x cosine y and e to the x sine y. Okay, so I have f equals e to the x cosine y I plus e to the x sine y j. So again, I do the same thing. So this means that we assume that, oh, you know what? This should have been, this is a little bit confusing up here. This should have been lowercase f because we're assuming it exists. And if it does exist, that's what the derivatives be. This is really annoying. Right, so this should be lowercase f. Right, we kind of assume that these derivatives exist or that this function exists, and if it does exist, we should get the same thing. If we don't get the same thing, this little f doesn't actually exist. Okay, so df dx is going to be this first component, right? We're assuming that this is equal to the gradient of something. So this is going to be e to the x cosine y, and df dy is e to the x sine y. So now if I do the y derivative of this, the derivative of this with respect to y is derivative of cosine is negative sine. I'm going to do the derivative of this with respect to x, and I get, let's see, so that's dx dy, and I get, that doesn't change, e to the x sine y. Okay, so these are not the same, right? They're close, they're negatives, but they're not the same. Okay, so this is not equal to this. So we conclude no f exists so that f equals the gradient of that function, right? Basically, there's no f where this is possible. So real quick, in terms of the textbook, and I believe he uses this in the lectures. Um, One second, Jose, I'll get to your question. So um, one, oh, so to compare this with things he put in the lectures, this is what he calls P, and this, oh sorry, and the other term is what he calls Q. Okay, so these are the what's typically used in the notation. Okay, but this is I think this works just fine. Okay, for the second one, why did you integrate with respect to dx dy? Okay, so for this one, I didn't integrate. I'm doing the derivatives. Um, right. So up here, I did the same thing. Right. First, I assume that the x component is df dx, and then I compute the y derivative of that. And then here, I assume that the second component is a y derivative, and I compute the x derivative of that. And I need them to be the same if I want to write this as the gradient of something. Okay, so I did the same thing here. I assume that the first component is the x derivative, and then I compute the y derivative of that, and then I do the same thing. So I assume that the y component is the y derivative, and I compute the x derivative of that, and then I check, are they the same? Okay, if they are the same, then I can write this as the gradient of something. I need to figure that out separately. And if they're not the same, can't be done. Okay, so let's look at this interesting example. Okay, so let's look at a very typical example. Newton's second law, right? F equals m r double prime, meaning F equals ma. All right, so the work done by this force, if you guys remember from physics, work is equal to force times distance, but we can also do it this way to adjust for not moving in a straight line. So this is going to be the work done by pushing something, but I don't know, pushing a box or something along a weird line like this. Okay. So I put this in, and let's expand this out. So this is the integral t0 t1. So we'll say that r of t0 is point A, and r of t1 is point B. Okay, so this is going to be m r double prime of t dot r prime of t dt, right? That's what dr is. Okay, but this I can write as this I can write as m over 2 t0 t1 of the derivative of r prime dot r prime dt. Right, if you work the derivative out for this, you'll find that it's the same thing. You just use the product rule. Actually, I'll do that real quick. So r prime dot r prime, right, I do the derivative of this, and I get r double prime dot r prime plus r prime dot r double prime. So that's 2 r prime r double prime dot r prime. So if I divide both sides by 2, I get this substitution that I did here, right? 1/2 of this derivative is equal to this. Okay, but now I'm integrating this with respect to dt, right? And this is an integral with respect to dt, so this is just going to be m over 2 r prime dot r prime evaluated from t0 to t1. Okay, so r prime though, that's just going to be the velocity, or yeah, so this is m over 2, or r prime dot r prime, that's the magnitude of r prime squared from t0 to t1, which gives me m over 2, right? The magnitude of r prime, that's going to be the velocity, but this is r prime of t1 squared minus m over 2 r prime of t1 squared. So does anybody recognize this term? Or what these terms are represent? No? Let me write it this way. R prime, norm of r prime squared. Well, norm of r prime, that's just the velocity. So this is going to be m over 2 v squared at 1 minus 1/2 m v squared at 0.0. This is just the change in kinetic energy. Kb minus Ka. Yeah, so the work done is just going to be the change in kinetic energy. Okay, so let's tie this back to line integrals. Oops, hold on. There we go. Okay, so we did this. Now, let's assume that F is a conservative vector field. So what does that mean? It means that we can take F and we can write this as the negative of some potential function. Okay, so now I'm going to work out the same thing. I had work equals integral of from A to B, or along this curve, of f dot dr. So this becomes the negative integral from t0 to t1 of gradient f r of t dot r prime t dt. All right, this is just like we've been doing. Okay, so this right here, if I scroll way back up, right, remember that the whole point of talking about this was that gradient of f dot r prime I can write as the derivative of f of r. So this I can write as the negative integral t0 t1 dt of f of r of t dt. So then I integrate this, and this just becomes, you know what, I'm sorry, I meant to put this as p, function p. So I'm going to go through and change that real quick, because it makes more sense for this example. P. Okay, so I do this integral, right, and I'm integrating a time derivative with respect to time, so this is just negative, and I just evaluate this function at the two endpoints. So that's p at r t0 minus p at r of t1. So I distribute the negatives so they swap orders, and this just becomes p at b minus p at a. Okay, so I have work, so work is equal to this, and work is also equal to this. Okay, so that means they must be equal to each other. So that means that I have, wait, did I do that negative sign right? I think I messed up the negative sign. Negative, this is, yeah, hang on, where's my negative sign wrong? Oh, because this should be T1, this should be T0. Okay, I got those backwards. So this is P of A minus P of B. There we go. Yeah, there we go. Okay, so they must be equal to each other. So I have K of B minus K of A equals, and remember this stood for the kinetic energy. This is equal to P of A minus P of B. So if I move this over to both sides and then move Ka over and move Pb over, so I get K of A plus P of A equals K of B plus P of B. Does anybody want to take a guess at what this P stands for? What this P represents? That's going to be that's going to be the potential energy. That's why we call this function, up here, right? The thing we're taking the gradient of, we call that the potential function, right? Because, kind of physically it represents the potential energy, right? So I said way up here, the thing we're taking the potential of, or taking the gradient of, that's our potential function. And notice when I have a conservative vector field, so this is a big if I have something like this, then the total energy, right, the kinetic plus potential, stays the same. So it kind of conserves energy, right? The energy stays the same. That's why we call it a conservative field. Okay, so also another interesting example of this is that, or illustration of this, is that because this is a line integral, and because we're dealing with a conservative field, it doesn't it doesn't matter what path you take if you want to figure out this work done. Right, the work done by this field is going to be the same no matter what path you take. You can go all the way around here, and that's going to be the same amount of work done as if you just went straight there, or if you went did some weird loop. It's going to be the same amount of work because for a conservative field, the line integral does not depend on which path you take. It only depends on the endpoints. Okay, so I know that was a little bit physicsy, but I think most of you guys are engineers, so hopefully that was okay. Um, any questions?